Hi everyone, we're going to continue where we left off with the second video for day 4. We're going to learn how to graph complex numbers. Now we know that for real numbers we use the real axis, right? We use the number line. For complex numbers, because I have two numbers associated with it, I have the real part and I have the imaginary part. So I'm going to use two number lines. And the easiest or the most obvious way to do that is x and y coordinates. So I'm going to call this the real part of z and the imaginary part of z. Now the real part of this complex number is 2 and the imaginary part is 1. So we call the arrow connecting from here to here can be thought of as the complex number, or even the point 2, 1 can be thought of as the complex number z1. In this case, instead of using x and y, I just label them as real part of z and imaginary part of z, which as we know are just real numbers. So that would be z1. Similarly, z2 would be -3, -2. z3 is -1. So the real part is -1, but the imaginary part is 0. So it's on the x-axis. Similarly, z4, the real part is 0 and the imaginary part is 3. So it's on the y-axis. So purely imaginary numbers lie on y-axis, and purely real numbers lie on y-axis, x-axis. Okay, so these would be like 2i, I, -i, √2i, pi I, 10i, so on. And these would be just real numbers you're familiar with. Because it's just a number line. So because we are dealing with two numbers, we use two number line. And the most familiar way of organizing these two number lines is x and y coordinate. And this should sort of give you an idea of where we are heading, because we just learned that rectangular coordinate systems can be converted to polar coordinate systems, which means that if I can view a complex number as a point on a rectangular grid, then I should also be able to view it as a point on the polar grid, which is going to be the focus of the next video. Let's look at some more graphing. Say it says graph complex numbers with a greater than or equal to 0. Now this may seem like look kind of complicated, but what is this saying? What is a? A is the real part, and this is the real part, and this is the imaginary part. Now in this structure, where is this true? If I am in quadrant 1, then the real part is positive. If I am in quadrant 2, the real part is positive. If I am in quadrant 3, the real part is negative. Oh, sorry, quadrant 2, the real part is also negative. And in quadrant 4, the real part is positive. So what this graph is going to be, instead of a shape, it's going to be an entire region. So any complex number here, has real part positive or 0. Similarly, what am I trying to plot here is numbers which have imaginary part positive. So I already know that imaginary part positive would be above, so quadrant 1, quadrant 2. But I also want the real part to be less than 1. And that's the real part. the real part less than 1, and the complex part positive would give me all of this. I cannot be here because even though the complex part, or sorry, the imaginary part is positive, the real part is more than 1. But right to the left of this line and above the x-axis, both these conditions are satisfied. So you have that the imaginary part is positive or 0 and the real part is less than 1. Now here's a bonus question. Take some complex numbers, plot them. Now multiply each of them by I and then plot the result. And then look at them pairwise and see, can you find any relation between them graphically? I'm going to not have the solution here, but I will be uploading the solution later on in the week. You can email me your attempts or your thoughts on what this could be to get the bonus point. Doesn't necessarily have to be correct. I just want to know what you tried and what you think about it. Now in Math 103, we learned this idea of absolute values of real number. And the way we learn what they are is that it represents the distance of the number from origin. And that's why both numbers 5 and negative 5 have absolute value 5. Similarly, both numbers 3 and negative 3 have absolute value 3 because they are both at a distance of 3 from the origin. Distance always being positive. So by analogy, we should be able to define absolute value of a complex number. And what it should represent is the distance from the origin. So if I take any complex number, a plus bi, that's the point. What is this distance? Oh, we have done this a few times now. If this is a comma b, this is a, and this is b. And r squared is exactly a squared plus b squared. So the distance is that. We give a special name to this. This is called the modulus of z, or the length of z, or the magnitude of z, or simply the absolute value of z. So what it is just the length. It's the distance from the origin, and it's square root of the real part, right? So if I were to write this more generally, it's the square of the real part of the complex number plus the square of the imaginary part taken under square root. So example here, 3 squared plus 4 squared, root 25 is 5. And we take the positive square root because it's a distance. 7 squared plus negative 1 squared, root 50. Negative 8 squared plus 3 squared, 64 plus 9, root 73. Just be careful that when you take the square of the negative, it's going to be positive. So what this really shows us is that the absolute value of a complex number equals the absolute value of its conjugate equals the absolute value of the same number with the real part negative and equals the absolute value, say both of these negative. Why? Because to find the absolute value, you take the squares and then you square root. And compare this with the analogy of real numbers. Yeah? In real numbers, absolute value of x is absolute value of negative x. So over here, what this says is, even if you make any one of them negative, it doesn't affect the absolute value. And what that says graphically is again something you've seen it in trigonometry. For any point AB, if you go across, you get negative AB. If you go down, you get negative A, negative B. And if you go across, you get A, negative B. And all of these points are a rectangle which lie on a circle. And the distance, the modulus of this complex number, on the graph, that's the radius of the circle. And the radius of the circle is always the same. So it remains unchanged. So the idea here is that the absolute value of a complex number behaves similar to absolute value of real number, in that you can interchange the positives, negatives, and it still remains the same. Now, because there are two numbers, there are four ways of doing it, as opposed to real numbers. Let's do a few more examples of graphs. Graph this complex number. Its absolute value is 1. So, a squared plus b squared is 1. A squared plus b squared is 1. What's that? That's a circle. You can also reason it in the same way as we talked about in the previous case. All numbers which are at a distance 1 from the origin are exactly the circle. So these are all numbers at distance 1 from origin. And you can see that if this was absolute value of x equals 1, you would get exactly two solutions on the number line, which are 1 and negative 1. Graph the complex numbers. Now, instead of an equality, I have less than. So I already know that everything on this circle has an absolute value 1. So everything inside this is going to have the absolute value less than 1. So when you have an inequality, you actually get a region and not just a shape. So this leads us to the question of what do complex numbers with a specified absolute value represent? We've already seen that they represent circles. So for different values of k, what they represent are concentric circles. Right? Now, where have we seen a picture like this before? We've seen this in polar coordinates for values of r. Remember? Different values of r, we get concentric circles. And for different values of absolute value of the complex numbers, we get concentric circles. So that gives us a notion that they might be related, which is what we're going to explore in the next video.